Any questions over the homework before we get started? Question on any of the homework so far?
I almost have all mine up.
Okay. So we're continuing on what we did Thursday with solving these logarithmic and exponential equations. Now the first one that we have here is an exponential. We are looking at 2 to the x equals 7. So we're trying to figure out 2 to what power gives us 7. Now one way we can go about doing this is we can grab a calculator and say 2 squared is 4, 2 cubed is 8. So that's too big. So now if we were going from here, we start up to approximating. So we could say 2 to the 2.5 is too small. 2 to the 2.7, still too small. 2 to the 2.8, getting closer. 2 to the 2.9, that's gotten too big because we're trying to get it to be 7. So then we'd go 2 to the 2.85. Still too big. 2 to the 2.84. Too big. 2 to the 2.8. We'll jump to 2. 2 to the 2.81. Was it 8 or? Make sure I didn't get too. So then we'd have to go 2 to the 2.805 and have to keep going here and approximating further and further out. But on a whole, that's very tedious and time consuming. It's not effective. So one of the first things we want to do is actually go about this a little bit differently. We want to get one base / term on each side. With bases, we want one base on either side, or one base, the variable with the base on one side, all of our numbers on the other. So 2 to the x equals 7 meets this condition. We got 2 to the x on one side, we got 7 on the other. We do not want them on the same side. Now the second step, I'm just going to call get variable out. Now I'm going to leave it in kind of these generic or general terms because in this case, we need to get the variable out of the exponent. When we talk about logarithms or logarithmic equations, we want to get the variable out of the logarithm. So if it's in an exponent, we need to get the variable out of the exponent. If it's in a logarithm, we need to get the variable out of the logarithm. So here, what we're going to do is the opposite operation. If it's an exponent, we're going to use logarithms. If it's a logarithm, we're going to use exponents. Now for this here, the logarithm that we use is going to be very specific. We want to use a logarithm whose base matches the base that the variable is in the exponent to. And here we're going to use log base 2. So we're going to apply log base 2 to both sides. And the reason we do this is, again, one of the properties we had earlier said that log base b of b to the x was x, and that is true. But since then, we've had our power property. And the power property says we can move an exponent inside the logarithm out to the front. So this is the same as x times log base 2 of 2. And it is still equal to log base 2 of 7. Now log base 2 of 2, our logarithm here. As we've talked about and worked with logarithms, really what a logarithm is saying, 2 to what power is 2? Our base of the logarithm to what exponent gives us what's inside the log. And well, log base 2 of 2, 2 to what power is 2? That'd be 1. Log base 2 of 2 is 1. So really this whole thing is going to become 1 times x is x. So really we have x is equal to log base 2 of 2. Questions on this so far? We ready for step number 3? Solve for x, solve for the variable. We need to get the variable by itself as our third and last step. Well, x equals log base 2 of 7. X is by itself, it is solved. Questions on this here? Now, this here, for all case and purposes, especially on the test, is going to be the correct answer. Now, we can find its approximate value. I can take the graphing calculator, go math, log base 2 of 7, and find out that it's 2.807354922, which we were on our way to getting. Or if we rounded it to 3 places, it'd be 2.807. And I will take both of those because those both are the same answer. But bare minimum, I want you to at least get here. If you get the decimal approximation wrong, I'm not going to count off for it. I'm not going to count it wrong because you got the decimal approximation wrong, especially if you gave me the log base 2 of 7. And I do this for a very particular reason. What did this question ask us to do? Solve each equation, yes? Need my highlighter. Is x equals log base 2 of 7 solved? Yeah. So we did what it said. We actually solved it. The whole process is to get here. Going from here to here, that's not solving it. That's using the calculator to find the approximation of what log base 2 of 7 is. That is not a part of, it is a part of solving, but it's not solving. You already solved it. If you got the decimal approximation wrong, that's not an error in solving, that's an error in plugging it into the calculator. So I'm not counting off on calculator errors if you've already solved it. Questions on this here? We ready for the next one? 3 to the x is equal to 8. Do we have one term on either side? Well, yeah, we have 3 to the x. That term's on one side. We have 8 on the other. Since we do have one term on either side, we can apply log to both sides. And I'm going to use log because the base we're using is not e. But what base do we need to apply to both sides? 3. We're going to apply log base 3. Because what we're able to do, properties of log say I can move the exponent to the front, telling me that log base 3 of 3 to the x is the same as x times log base 3 of 3 is equal to log base 3 of 8. And as we said before, log base 3 of 3 is what? This whole thing is 1. Because when the base and what's inside are the same, it's going to reduce to 1, which is telling me I have 1 times x, which is just x. Telling me x is equal to log base 3 of 8. X is by itself, so it is solved. We don't have to do anything else to it. That's the final answer there. Questions on this here? Now, if we wanted to find the decimal approximation, we can do it just like we did on the last one. Now, say you don't have a graphing calculator, well, we can still find the approximate value using the change of base. Because log base b of x is equal to log of x over log of b, or the natural log of x over the natural log of b. So according to the change of base, this would be the same as saying log of 8 over log of 3. Log of 8 divided by log of 3, which is 1.893. And that would be our approximate value of this here. So that's telling me 3 to this here should give me 8. So if I go 3 to the, it tells me it is indeed 8. Questions on this here? We're ready for the next one. 7 to the 9x equals 15. Do we have one term on either side? Oh yeah, we have one term on either side. We're good there. So that means I can apply my log to both sides. And specifically, it's going to be log base 7. Because our log base 7 of 7 to the 9x, as we said, the 9x would move to the front. Which tells us that we have 9x times log base 7 of 7. And again, log base 7 of 7 is just 1. 1 times 9x is 9x. Yes? X is by itself, so we're done, correct? Oh wait, x is not by itself, is it? What do we need to do to solve for x now? Divide both sides by 9. So 9x divided by 9 would be x. Log base 7 of 15 divided by 9 is what we get, because we cannot divide the log base 7 of 15, or the 15 part of it, by 9, because log base 7 of 9, 15 is a number, is a value. And we're taking whatever that value is and dividing it by 9. Now, we did have our properties of logarithms, our quotient property, but that said log base b of m divided by n is equal to log base b of m minus log base b of m. That is not what we're doing here. It's not dividing two things inside of a log. But this here, log base 7 of 15 divided by 9 is the solution, is the value of x that would make this true. Yeah. And if we wanted to find the decimal approximation, we can go alpha y equals enter. Math. Log base 7 of 15 over 9. Telling us that 0.1546291677 or 0.155 is the decimal approximation of this here. We could still do the change of base and have log of 15 over log of 7. 15 over log of 7. and take that divided by 9, and we get the exact same thing. I would not do a decimal approximation of it, because I wouldn't want to take 1.392 and divide it by 9. We would get close, but as we can see here, there is a difference, especially if we go to the 5th or 6th decimal place. The value changes significantly. Because luckily on the previous one, it actually did the division for us. The other option is just putting it as fractions and fractions. Questions on this here? Do we have one term on either side? Yes, even though we have the 3x plus 7 on the right-hand side, because it is in the exponent, it is still a single term. Which means we can apply this log to both sides. And because the base of the left-hand side is 5, we can apply log base 5 to both sides. And log base 5 of 5 to the 3x plus 7. 3x plus 7 comes to the front, and it still be multiplied by our log base 5 of 5. And yes, log base 5 of 5 is just 1. Questions on this here? Questions on anything we've done so far? Is x by itself? No? What can we do to both sides? We want to subtract 7 first. The left-hand side would become 3x because those would cancel, yes? On the right-hand side, we'd have log base 5 of what? Would this be 304? No. It's still 311 minus 7. Because again, as I've said, or I said earlier, log base 5 of 311 has a value. And we're not taking 7 away from the 311. We're taking 7 away from the value of log base 5 of 311. So whatever value power 5 is 2 to get to 311, that's what we're taking 7 away from, not the 311. X is not by itself, so we need to divide both sides by 3, telling us x is equal to log base 5 of 311 minus 7 over 3. So for the most part, think of log base 5 of 311, this term, as a specific term. It's a number. It is a value. So we're not going to mess with the things or numbers inside the parentheses. We're not going to do anything, especially when we're adding, subtracting, multiplying, or dividing it. Does that make sense? Now, if we wanted to do this in the 30xs, what we can do, log of 311 over log of 5, minus 7 from it, and divide it by 3. Negative 1.144555382, or negative 1.145. So that tells me 3, or 5, to the 3, parentheses, negative 1.145 plus 7 should equal 311. Now, is it going to equal exactly 311? Depending on how the calculator approximates, because negative 1.145 is not the exact value of this solution. It is the approximate value, so it will get us to approximately the correct value. Now, if I wanted it to be a little more precise, we can do 3 parentheses, come up here, grab that whole thing, plus 7, and it'll get me pretty darn close. Because again, even that's still an approximation. So it's approximately close to what we need it to be. The only true way is rewriting it or checking it with 5 to the 3 times log base 5 of 311 minus 7 over 3 plus 7. I have to plug the whole thing back in to get it exact. Questions on this here? Now, the nice thing with exponents, it doesn't matter what the value of x is that we plug into an exponent. As long as it's a real number, it's going to work. So it can be positive, it can be negative, it can be fractional, it can be irrational. Exponent doesn't make a big difference. Do we want to do this one or the next one? Doesn't matter. 36 to 36, 12 to the 12x minus 5 equals 4026. Is there one term on either side? Yes. I feel like there's something else on this page, but that's fine. $40.26. Now, since there's one term on either side, we can go on and apply our logarithm to both sides. So we can apply log base 36
Time to release the baseball boys?
to both sides. And on the left-hand side, we would get 12x minus 5 times our log base 36 of 36 equals log base 36 of 40.26. And as we said before, log base 36 of 36 is just 1. What would we need to do to get x by itself? First thing we can do is add 5 to both sides, telling us 12x is equal to log base 36 of 40.26 plus 5. And then lastly, we would divide both sides by 12. Log base 36 of 40.26. Yep. Plus 5 over 12. 0.60969222175, or 0.670. 6.1. Don't know where I got the 7 from. 0.610. Now, yes, we do need that 0 to signify we rounded to the third decimal place, and that third decimal place went from a 9 to a 0. It rounded up. Yep, anytime one of those decimal essentially goes from 9 to the next 10 and zeroes out, we got to put it. Even if both of these rounded up, because we had 9, the fourth decimal says we round up. First 9 becomes 10, so 0 carry the 1. Next 9 becomes 10, 0 carry the 1. We still put both zeros to signify we rounded to the third spot. Makes sense? It's 6.61. 0. Questions on these so far? This one's a little bit different because our base is E. Also, we don't have one term on either side. Because on the left-hand side, we do have the E, but we also have it being multiplied by 4, and 7 is being subtracted from that product. So the first thing we're going to have to do is add 7 to both sides. We need to get this E to be by itself. So if I add 7 to both sides, the negative 7 plus 7 will simplify out, leaving us with 4e to the negative 0.3x. Is e by itself? No, we got to do what? Divide both sides by 4. 4e, or 4 and 4 will simplify, leaving us with e to the negative 0.3x is equal to 5. Now do we have one term on either side? So now we can move on to getting that variable out of the exponent. And what log will we apply to both sides? Log base e, or the natural log. And just like with our logarithms, LOGs, the exponent will move to the front, telling us that negative 0.3x times the natural log of e equals the natural log of 5. Yes? So what is the natural log of e? 1. That is one way I remember the fact that it is indeed 1. So it's telling us that negative 0.3x is equal to the natural log of 5. So for x, we would need to what? We need to divide by negative 0.3. Negative 0.3x divided by negative 0.3 would give us just x is equal to the natural log of 5 over negative 0.3. Telling us that it is going to be negative 0.53647 or negative 5.365. Yep. Questions on this here? Three e to the x minus 4 equals 8. What do we need to do first? Add 4. Telling me 3e to the x is equal to 12. And we would divide both sides by 3. Telling me e to the x is equal to 4. We have one base on either side, so we can now apply the natural log, our ln, to both sides. The x would move to the front, Really, natural log of 1e is just 1. Telling me that natural log of x, not natural log of x is equal to the natural log of 4. Or x is approximately 1.386. We agree? Questions on these here? Do we feel comfortable solving these with E? This one, if we did it, E is already by itself, so we'd take the natural log of both sides, add 3, divide by 4, telling us that x should equal the natural log of 19 plus 3 divided by 4. But that's about it. Now, the last set of type, or the last type we're going to look at for today, is going to be logarithms. Now, when we were solving exponentials just a minute ago, we wanted one base on either side. With logarithms, I want one log, especially if we have more than one logs. We would normally, our one-to-one property says we put one log on either side, simplified it out. And that works fine as long as I don't have a number outside of the log, a number by itself. Because as soon as we get that, like this 3 here, I need all the logarithms on one side. Now, if I have 2 logarithms and a number outside, I get them together. We use our properties of logarithms to make them 1, so that we have one term on either side. And then we're going to use exponentials to simplify these out, or at least try to anyways. Because since the base of this log is 2, I'm going to put both sides to the base of 2. Now the right-hand side, we're going to have 2 to the third. The left-hand side, since the base 2 that we applied to it, and the base of the log is also 2, these two are going to simplify out, leaving us with what's inside. So when I put both sides to the base of 2, our 2 to the log base 2 of 5x minus 17 is going to be 5x minus 17. Our other side we have is 2 to the third. Now, is 2 to the third power a nice number? Yes. Because 2 to the third is 8. Now, when I say nice number, I mean 2 things. One, we don't have an irrational number. We don't have a non-terminating, non-repeating decimal. Or the number is just too big. So if it had told us that we actually have 2 to the 70th power, that's way too big for me to be able to write out. Because 2 to the 70th, we're talking about a number like this here. Goes 2017. So we're really talking about the 17th trillion. I don't know, I don't have that number memorized of what that would be, because that'd be heptadecillion. Probably got that completely wrong. But it's going to be a massively big number. 8? No. Very nice. Now we just need to solve. So the first thing we can do is add 17 to both sides, telling us that 5x is equal to 25. Then we would divide both sides by 5, telling us x is equal to 5. There is no approximating, it is just 5. Which is telling us that log base 2 of 5 times 5 minus 17 equals 3. And if we did this and we wanted to check it and make sure it works, 5 times 5 is 25. 25 minus 17 is 8. So we're saying that 2 to the third power does give us 8. That works. And the main reason we would want to check it is to make sure after we plug x in that this number here does not turn into a negative. Because I cannot take the log of a negative or 0. And for the most part, when I start out with a single log, we're not having to do our properties of logarithms. We don't cause, an error does not come into play. We don't have to worry about restrictions. Questions on this here? I believe we have 2 left. So log base 3 of 10x minus 9 equals 4. For this one here, we do have a single log on one side. We have a single term on the other. So what are we going to put both sides to the base of? 3, because our 3 to the log base 3, these would cancel, leaving us with 10x minus 9 equals 3 to the 4th power. And if we calculate what 3 to the 4th power is, we see that it is indeed 81. Bigger than the last time, but it's still a nice number. Now we just need to solve for x. First thing we can do is add 9 to both sides. Because our negative 9 plus 9 would cancel. 81 plus 9 is 90. Last but not least, we would divide both sides by 10, telling us x is equal to 9. And that would work back in there. That's fine. Because if I wanted to grab a calculator, I could say math log base 3 of 10 times 9 minus 9, and it does indeed give us 4. If it didn't, or there was an error that occurred, it would tell us domain error division. It will throw that error out. Well, we have time, might as well. We're going to put both sides to the base of 2, and we know that those will cancel, telling me that x minus 6 is equal to 32. Add 6 to both sides, telling me x is equal to 38. Now we can have some more complicated. We can have some that have multiple answers, and those normally come in when we have quadratic equations or others that get applied to it, because then we have to solve the quadratic. But realistically, this operations are what we have to do to solve these logarithms isn't more than that. Really, the complexity comes not so much in the getting the x out of the variable, that step, and just solving for x.